Okay, so that should be calibrated nicely there, and when I take this off it will go back to 0. Good. And now we can weigh some things. So let's try this AA battery. Looks like that's 25 grams. How much is the Sharpie? Sharpie is, whoops, got to get it in the right place. It's probably 8 grams if I could get it to sit a little bit more central. There we go, 8 grams. And the screwdriver looks like that's about 21.5 grams. Oh, hello there. You caught me in the middle of weighing some things here at my desk. I just had a sudden burning desire to find out what this Sharpie weighed. No, I'm testing this very fancy load cell that I made out of a piece of scrap aluminium and some of these tiny little strain gauges there. There's 2 on the top, 2 on the bottom, and they are connected by 4 wires which go over to this load cell amplifier. And then off to the left there is an I/O mixer which is reading in the signals from here and displaying on the screen there. So let's have a little bit more of a look at how this all works. You may have seen load cells before. They typically look a bit more like this. Well, there's various arrangements of them, but this is a fairly common one. It's just a bar of aluminium, and we've got this sort of white rubbery, ever so slightly soft substance that's hiding something underneath, and my camera doesn't want to focus on this very well for some reason. But anyway, we've got the same 4 wires coming in from here, and on the top and the bottom we can see, well, we can't see much, but we can see that there's wires going into the top part, and then there's wires going into the bottom part as well. And this piece of aluminium has been weakened so that right here in the middle where these white patches are, it'll be more susceptible to stretching along the top and squashing or compressing along the bottom, or vice versa, depending on which way you're trying to bend it. But the point is that most of the stress is going to be concentrated in this little bit, or most of the effect of the change in shape of the aluminium is going to be concentrated on this little patch here. And right underneath here is where they've stuck some strain gauges. And come on, camera, man, don't know why my camera's misbehaving so badly, but anyway, these are the strain gauges that are underneath the white stuff. There'll be something very similar to this, I think. These are the ones that I got from AliExpress. They're very cheap. I think these were like $3 for a pack of 8. Typically you'll find them in multiples of 4, I think. And all they are is just a little resistor placed on a very thin, flexible film of some sort of plastic. And if you're smart, you'll buy the ones like this that are pre-soldered to save yourself a little bit of time. But you can probably see there, hopefully, it's just a little very, very thin trace that goes backwards and forwards along there. And they're very, very small. They're 7 by 4 millimeters, these ones are anyway. And part of the point of these is that they're supposed to be very, very uniform in the resistance that they have. And these ones are rated for 300 ohms. And you need to arrange it, obviously, so that the lengthways traces are in the direction that the aluminium is going to be bending. And they're stuck on there with super glue, which seems to be the best thing to use, apparently. And this is an HX711 load cell. And then that, like I say, was connected to an I/O mixer over there. But the reading of this load cell amplifier is not really the focus of this video. I'll assume that people who are interested in making their own load cells probably have already figured out the software side of reading the values from a load cell, like a standard one off the shelf. So I'm not really going to cover that in this video. We're just going to look at sticking these things on and having a little practice at that and seeing if we can make a really nice custom load cell. So the end goal of all this is to make my pick and place machine capable of probing anywhere in its region of movement just by using the load cell to go down until it's touched something. And the way I'm hoping to do that is by placing strain gauges on the top and the bottom of this thin piece here, so it's connecting from the belt to the motor itself. So this is going up and down like that. But the motive force for moving up and down goes through this thin piece there. So the idea is that when it moves downwards and it gets stuck on something or it touches something, this bit will bend ever so slightly and the strain gauges will be able to sense that it's touching something. I'm not super confident that it's going to work very well, but I thought it would be very interesting. It would be a fantastic feature to have if it does work. So that's why I wanted to give it a try. There may be other issues to deal with too, like when the machine starts moving very quickly, right as it starts moving, it might actually sense a little bit of bending
in this thin piece here, and it would detect that as a touch on the bottom incorrectly. So somewhere in the software we might have to like account for that as well. But anyway, I'll just make this load cell first, and then we'll figure out those problems later, if this even works at all.
Let's have a little look at the theory about how this all works. So we have 4 resistors, and we need to connect them in this kind of a circuit. It's just a square or a circle, I suppose. And as I mentioned before, these are all exactly the same resistance, or that's what we want them to be. They're going to be very, very close to that anyway. And if we connect a voltage across the opposite corners of this square, for example 10 volts, what we have here is 2 voltage dividers, one on each side. And if everything was all perfectly the same, then we would expect to see exactly 5 volts on each side. And we can measure the difference in voltage between those 2 middle points. In this case it would be just 0 volts. But we can use that to figure out how much these resistors are stretching or compressing, because when these resistors, these strain gauges, when they get stretched out to be longer, their resistance increases. So for example, if we stretch the one on the top right, that would result in the right hand side middle point being slightly less than 5 volts, say 4.98 or so. And then the difference between those 2 middle points would be 0.02. And then if we stretch the one on the top left, that would cancel that out again, and the difference would be back to 0. But what if we stretch the one in the bottom left, like this? That would result in the left-hand point being slightly higher than 5 volts, say 5.02 for example. And then the difference grows, so it's 0.04 now. And then on top of that, if we also compressed the other 2 resistors, so the top left and the bottom right, that would even further increase the difference. So as an example, I'm just picking some random numbers here, but I'm assuming that for each compression or stretching we're getting 0.02 volts difference. So the total of this would be 0.08 volts difference across the 2 middle pieces. In reality, the difference between these 2 voltages is much, much smaller. It's something on the order of millivolts is what we're measuring. So that's why we need that special load cell amplifier to measure such a small difference in voltages. But as a result of all this, we can figure out how much that piece of aluminium is bending, and by looking at the voltage difference from 2 known loads, for example 0 grams and 100 grams, like I was doing at the beginning of this video, we can just use that voltage difference to relate that to an actual force in the real world, like grams. Now, to translate that into how we can actually connect these strain gauges together, I thought I might share a little diagram that I made, because it took me an embarrassingly long time to get this right. Actually, I made a mistake or 2 the first time I tried it. And I like this arrangement because it has all the output wires coming along one side of the aluminium, and it keeps the wires that cross from the top to the bottom roughly the same length. You don't want to have a wire that's too short and then one that's all long and dangly. But anyway, so the plan is we've got obviously 2 load cells on each side of the aluminium, and we want to take the outside pad of the top and connect that to the inside pad of the strain gauge directly below it, like that. And I've deliberately drawn these lines with a curve like that instead of just going straight between them, because you have to keep in mind this has to wrap around the outside of the aluminium. You can't just go in a straight line from here to here, and you have to pick one side or the other. So we want to pick the short side instead of going, say, from here all the way over here and then back like that. And then the next connection is from the inside pad of the top to the outside pad of the strain gauge that is opposite it on the bottom. So it's going to be like this, and that does require a slightly longer connection, but should be fine in my case. And then for the connections to the load cell amplifier, these are typically called E plus and E minus, and then A plus and A minus, I think, on most of the ones I've seen. It doesn't really matter what the plus and minuses are. You can just swap them around if the values are not going the way that you prefer. And you can also swap the A's to the E's. That doesn't matter either, because as we saw before, the circuit is perfectly symmetrical in every way. You can also swap the values in your software if you want it to be the reverse of the direction that it's going as well. Here's some footage I took when I was machining my custom load cell. It's quite a complex little task, this one. It takes 2 setups and 4 tool changes, so it's a bit of a pain in the ass, and then I have to do a bit of hacksawing as well at the end of it. And I'm actually thinking that if I want to make another one of these in the future, I might just try the JLC CNC service, so we can sort of upload your plan to JLC CNC and they'll machine this thing and send it to you. And I'm curious to see how they would deal with a complex thing like this, and whether they can actually get that slit in the side that I had to do with a hacksaw. I think that after I upload this plan, somebody will probably send me an email saying, oh, actually there's a bit of a problem with this one, we can't really do that. It's kind of what I'm expecting, but I think I might give it a try someday anyway, just to see how it turns out and what happens. The thing about the JLC CNC service is that if you just want one made, it's kind of expensive. If you want about 10, it's not too bad. Anyway, so this is what I've ended up with. I think I just showed you all this basically, and now it's been cut off there and got some holes threaded so you can put some screws to clamp onto the belt. So the idea is I'm going to put 2 strain gauges on each side of this, and I made a little bit of a boo-boo here because I hadn't actually investigated the Wheatstone bridge or the strain gauge stuff very well at the time that I designed this. So the piece of aluminium where I'm going to stick these is not quite wide enough to fit 2 of them on. Actually, I think it might be, but it's going to be pretty tight. I think it'll be okay. But if I was doing this in future, I might make this little flat strip in the middle a little bit wider than I have. But anyway, before I do this one, I'm going to make another test like this, just a rough one. I'm going to make it out of this bar this time because I want to get a little bit more practice at it just in case I screw this up, because once you've super glued those strain gauges on there, they're probably going to be very difficult to get off. So I just want to make sure I get it right, and I'll probably get it right the 3rd time rather than the 2nd time. So I'm going to go with this. This is also 3mm thick, same as my piece over here. By the way, if anybody feels like asking me what is a suitable thickness and length of aluminium to use, I really have no idea. I just played around with this, and as you can see, it's not a very nice piece of aluminium. It's just one that was in my offcuts bin. And what I can tell you is that the more you're able to bend it, the more numbers, or the more the numbers will change coming from the load cell, so you'll get more resolution. But then the more you bend it, the less, I guess, it's going to bounce back to where it was before. So you need to strike a sweet spot between how much you bend it and the resolution that you can get from your measurements. But anyway, so this is 3mm thick as well. It's much shorter, so I can't get as much leverage, but I want to see if I can still get a reasonable resolution from this. And another thing I want to try with my 2nd attempt is a different method of putting some goo on the top here to protect it after it's done. So I tried this liquid electrical tape on that one. That was my first choice, and it seems to be okay. I put this on yesterday. It's probably just the perfect amount of sort of rubbery, springy feeling. You don't want it to be too hard, so you don't want to use something like epoxy, because the load cell has to be able to, the strain gauge has to be able to sort of stretch underneath it, so it has to be able to move a little bit. So this is probably pretty good actually, but unfortunately this container that I've got here is all dried up. The other thing is it has a very strong smell of acetone, so I wasn't sure if it's going to mess up the plastic of the strain gauges. But I think it will be alright. Like, it's still running perfectly fine. The numbers are coming out of this just like they were yesterday. But I thought I might try this for my 2nd one and see how that goes. This is not really ideal either. I think maybe some silicone kind of sealant would be alright, but I did a little test of this here and seems to be okay. This also has a slight bit of springiness to it, probably not quite as much as I'd want, but it does actually feel quite close to the stuff that's on the load cell, like their store-bought load cell. So I'll try this on my 2nd attempt on this bar and we'll see how that goes. I was just saying that I don't know much about how certain thicknesses of aluminium might respond to being bent, but then I remembered that I did actually spend quite a bit of time investigating how this particular piece of aluminium might behave. So that's what we're looking at here. This is FreeCAD, and FreeCAD has a very nice FEM analysis tool, and it is free. So I thought I'd give this a try, and I brought my model into FreeCAD and placed some stresses on it, and sure enough we can see that the stress is all concentrated in this thinnest part. And if we look at it from the side, we can see that it's just bending slightly, and this is with 600 grams of force. And the reason I went with 600 grams for my test is because the spring inside the nozzle just starts to compress at about 600 grams. So I wanted to make this little thin piece of aluminium in the middle thick enough so that it would just start to bend, like you can see it's just slightly bending at 600 grams, and I figured that would be about right. And then I machined it to be slightly thicker than that, just for a little bit of safety, because I figured maybe I could sand it down a little bit or something. And I also investigated what it would be like without these rounded fillets. This would have required a different setup, because I was still thinking about how I was going to actually machine this. And this is basically, the stress is the same, but it's spread over a larger area, so it doesn't get concentrated into the middle as much. So this is not really as ideal. It bends about the same amount. But if we go back to this one, we can see, if we compare this with that, the fillets cause the stress to be concentrated in the middle, and I think this is more what you want, because we don't want to break this, right? So the fillets help keep the whole thing relatively strong, stronger than this one at least, I think. But more to the point, it concentrates the stress that we're trying to sense right underneath where the strain gauge is going to be. So as long as this patch in the middle is large enough to hold your strain gauges, then I think this is the way to go. Now, as far as gluing the strain gauges onto here goes, I'll put a link in the description to a video where I learned how to do this, and you can look at that for a much better overview of everything. But just to sum it up here, basically we want to make this surface as clean and smooth as possible, so that every little movement that the aluminium makes, the strain gauge will also be moving as well. They need to be one and the same as far as movement goes anyway. And we do that by making this as smooth and clean as possible. So you'd want to use some very, very fine sandpaper to sand that. I didn't bother doing that on this one, and it seems to work perfectly okay. And probably it'll be fine on this one too. But I will use sandpaper this time because this is going to be my practice run for the real one. And the real one I definitely will need to sand, because if we can focus on here a little bit, there we go. Yeah, so you can see it's not particularly smooth on the parts where it needs to be smooth. So I'm going to have to somehow get my finger in here and sand that smooth. You don't really need to be as fastidious about this as I'm going over here. It will probably work fine if you do it a bit rougher. But from what I understand, the better bond you can get, the longer it will last. And keep in mind that this thing's going to be bending backwards and forwards over and over and over and over. And gradually over time, I think it gets less accurate or something like that. So you might as well try and do it nice. And since I've made this fancy thing, I want to make that one as nice as I can get it. So then to clean it, I use these Q-tips and dip these in acetone. I think IPA might be okay as well, but acetone certainly smells like it means business, doesn't it? So then you just rub this on here nice and firmly, and you'll see some grey stuff coming on, and just do that over and over again until there's no more grey stuff coming off. And don't touch it with your fingers, because apparently some finger oil, whatever gets on there, and then the bond will be compromised. And then ideally you want to take a piece of clean gauze to wipe any last little bits of fluff off. So I think some of this fluff could get in between the aluminium and the strain gauge, and you're trying to prevent that. I don't have any gauze, so I'm not going to do that. And then we take this super glue. Doesn't need to be this one, could be just any super glue, but I was looking around for what might be the best thing for this particular job, and this was mentioned as one that would be quite good, and it was available locally. So I splashed out and got this because it makes me feel like I'm making something important instead of just some crappy thing thrown together hastily. And then you take a bit of sellotape and you stick your strain gauge, or strain gauges, I guess. I might try doing 2 at a time this time. Stick them on the sellotape, and then use the sellotape, or put a little drop of glue on there, of course. You don't need much, just a little drop is enough. And then use the sellotape to roll like that, so that you don't get any air bubbles in between. So you want to sort of start from one side and squash it down like that, so that the air bubbles come out. In this case it will be coming towards me. And the sellotape is just there to make sure that you don't stick your finger to the aluminium. This sellotape is kind of crappy. It's not very sticky, but that's actually perfect for this job, because you want to make sure that once you've done that, you can still remove the sellotape. And I found it's best to do that before the super glue dries. That'll do. Remember to put these upside down when you put them on the sellotape, not that way. That way with the solder pads facing down. I'm going to try putting a piece of masking tape here so that the
leads don't get stuck down to the aluminium too much. The other nice thing about this is it lets me put a visible mark that I can use to line things up. Let's put that there. So now I know exactly where my drop of glue needs to go. And whoops, oh shit. This glue is very enthusiastic. I wasn't expecting that drop to come out there. Oh shit. Okay, that's probably way too much. So now we should be able to just go like that, and I can see that even though that drop was in the middle, it spread out all the way across. And now we can just go like this. Peeling it back perfectly sideways like this is the best way to do it. You don't want to pull it upwards. Yeah, when we get to where the glue was, it comes off nice and easily, see? Okay, we're good.
After soldering those from the top across to the bottom, you should have something like this. And so this is the other 4 connections soldered to the load cell amplifier. I'm using an HX717 here actually. This is one of my little breakout boards that I designed. Can we focus on that there? Maybe just see it says HX717, it's upside down. Okay, so I did a rough calibration of that, and now you can see we're getting some sensible numbers coming out of this. And if we put my 100 gram weight on here, have to put it right about there, we should get 100 grams. Ooh, nice. And then these things that we weighed before, it's hard to get it in exactly the right spot. Also, for some reason I've chosen 3 things that are round and they want to roll off the end, which was kind of dumb. But anyway, I think this is 25 grams before, so everything's reading slightly higher. This was 8 or so. 10 grams, yeah, so it was 8 before and now it's 10. So I think this is just a consequence of it not being able to get things in quite the right position. Okay, so here's how that ended up. It looks a bit scraggly with these wires on the top, and it looks even more scraggly on the bottom. They're kind of long, but it's a little bit awkward to remove the enamel from them to make them shorter. So I'm just using the whole length of it because the end of these wires came pre-tinned, so it's very easy to solder if you're using the very end of it. But if you want to make it shorter and solder part way along the wire, it's not so easy. And they're very delicate, so I'm just going to leave it like that, I think. And I'll bend that around a bit more and cover it with some of that goop so that it doesn't get pulled or bumped or knocked while it's being used. And in order to make this easily connectable to the load cell amplifier, which is going to sit on top of the head, I added some pins there, and then the E plus and E minus and whatever, those are all going to just be connected under the bottom like that. And I'll probably put some goop all the way around wherever these tiny little wires are, just so that they don't get damaged. And just testing that out here, I had to clamp it over the side of the edge of the bench, and I've calibrated it, so that's 100 grams, 0 grams, and I can push on it here to something about 50 grams. Let's try if I can get 50 grams. Oh, it's trickier than I thought. But you can see I can hold it at least somewhere around 50 to 60 grams. Seems to have reasonable resolution despite the lever arm being very short. But what I noticed is that when I try and put this back on, it's very difficult, or it's more difficult now, to get it at the exact same distance away as it was when I calibrated it. See, it's only 82 because it's very, very sensitive to the position now. Need to get it right right there to get it back to 100. But I think you can see that it's working okay. Okay, I've reattached the load cell to the machine. I didn't put any goop on it yet. I'll wait and see how the other one turns out before I permanently put it on this one. And to calibrate this, I just used the little set of scales like that and pressed down on the scales to like about 100 grams or so, and then used that as a calibration. And it's about what I expected. If it starts moving too quickly, the jerk of the motion triggers a touch, like a probing success event. And so I had to turn the jerk down to really, really slow speed. And the other problem I had was that
when it this stuff up the top here, these cables, if they get pulled on, they also act as, it'll sense that the probing has touched something at the bottom, even though all that's happened is this cable got a little bit tight. So have to be very careful with that, and we have to go very slow. So it's not as cool as I'd hoped it would be, but let's run one here. Okay, see what I mean? It's quite slow, but we can turn this to a different height, run it again. Hopefully it doesn't get stuck on anything. There we go. So it's probed those two heights there, and this is just a block of aluminium, but it could be anything, anywhere inside the workspace of the machine. So I think that's pretty cool. And even if it's slow, it's a heck of a lot easier than having to do that manually by jogging and using your eyes to check everything. Oh, and the other caveat that I had to do is, instead of detecting any touch more than 0 grams, I had to set it up to 30 grams. So I guess the thing that you're probing does need to have a certain amount of solidness to it, because it has to be able to support 30 grams of force before the probe will trigger. But that should be okay for most of the things I need to probe. So that's going to do it for this video. I hope that was interesting for somebody. Here's the load cell in all its glory, stuck on the machine again, with all the little scraggly bits of wire. It's not on there very well at the moment. You can see the wires just coming over the side directly into this other rat's nest over there, but eventually I will put it through this sort of drag chain kind of thing like that, and I'll have to fix the things that go down onto the head now, like this tube and this wire and this other wire, will have to be fixed somewhere around about here, so that as the head moves up and down, those wires will be nice and loose, because we don't want them to be getting tight in the middle of while it's probing. And it remains to be seen how useful this actually is in practice. I think it's going to be quite useful, but anyway, that's going to be a story for another day. So I'll just thank you for watching this video, and see you next time.